Okay, so let's talk about atomic radius again. What happens to atomic radius as you go from left to right? Who remembers? The nucleus gets bigger, but one of the things that we found out, which Marielle can relate to because she's Latina, is that as the nucleus gets bigger, the nucleus becomes more attractive to the atoms, to the electrons of the atom, so the electrons will actually get closer and closer and closer. So as you go from left to right, the atomic radius decreases for atoms. As you go down, the nucleus gets significantly bigger. But along with bigger nucleus, you have more electrons, right? Let me make this a little bit smaller, or else a little bit bigger. There we go. Okay, so this is lithium, 3 boyfriends. So we go down, sodium has 11 boyfriends. What does that mean? If you're the 11th boyfriend, what does that mean to you?
Once every 11 days.
Okay, Silas, you need to make that go away. Don't care. Don't care. Thank you. Okay, so as you go down, the number of electrons increases. What do we call this effect that you have the more boyfriends are between you and Kate Upton? Yes? Shielding effect. So that means that the greater the shielding effect, the greater the atom is going to be. So atomic radius increases significantly as you go down the column. Okay, so here Noah is the 37th boyfriend of 37 of Kate Upton. Yeah. Okay, Noah, you don't ever see Kate Upton the way it is now, right? Okay, what if you saw her every 37 days?
It's like 12 times a year.
Okay, right now it's nothing. 12 times a year. Alec, 12 times a year. Kate Upton, would you like to see her, go on a date with her 12 times a year? All right, thank you. He's more realistic. Okay, so, but he's way out there. Alec knows that he's the 37th boyfriend of 37. So, Alec, what would happen if this atom with a huge, plump nuclei was to come by but only have 12 boyfriends? Yes. So what do you think your choices are stay with Kate, as good looking as she is, but knowing that 37 of 37, or go with this other model that only has 12 boyfriends. Giselle. Whoever Giselle is, I don't know.
Tom Brady's
Oh, not Tom Brady. She's already married. Someone from Victoria's Secret. I don't know. One of those girls. Yes? I mean, it's not Kate Upton, but it's Victoria's Secret model. Okay, so what happens is it doesn't take much energy at all for Alec to be ripped away. Why? Because he's way out there. He is way out there alone, very, very far away from the attractive nuclei. This tendency of electrons to be ripped away is what we call ionization energy. So the second property we're going to look at is ionization energy. Ionization energy is the energy required to remove Alec, the most loosely held electron in the outer shell. The amount of energy required to remove the most loosely held electron in the outer shell. This is very abstract, So the best way to think of this is by using a metaphor. Okay? So, let's see. Football player Ryan, right? No. Let's use mortal, because he's a quarterback. Mortal. So you take off running. How are you going to hold on to the ball so that monsters like Ryan don't take it away from you? Close to the body. Absolutely correct. If you're holding on with both arms to that ball, how much energy will the Neanderthals like Ryan going to have to expend in order to take it away from you? A lot. Okay? Same principle in basketball. Are you going to be basketballing with the ball really far away from you? No. It's going to get taken away. How about soccering? Those of you who are soccer people. Soccering. So you're soccering, so you hit the ball and then you run and then you hit the ball again and then you run to it and then no. You keep the ball close. So in all these sports where you want to avoid having the ball ripped away from you, you want to keep it close to your body. The closer it is to your body, the more energy somebody's going to have to expend in order to take it away. Yes?
Could you think of it at all, or this would be crazy, like think of it like a blooming rose, have the petals on the outside you can pull off really easily, but as you get closer...
I like that. That's right.
Hard, they stick.
A blooming rose. The further away the petals are from the middle, the easier it is to pull away, while the closer it is, the harder it is to peel it away. Okay. I like hers though. Okay, so what can we say? Which one of these two atoms is going to have a higher ionization energy?
That one.
Why?
Because it's smaller.
It's smaller. The electron is closer to the nucleus. The harder it is to rip it away. So what we find is that atomic radius and ionization energy are complete opposite. As you go from left to right, atomic radius does what? Smaller. What does ionization energy generally do? Gets bigger. As you go down, atomic radius gets bigger. What does ionization energy? I had to use the word generally because, look, bigger, smaller, bigger, bigger, smaller, bigger, bigger. Something weird happens here and happens here. Let me give you a clue. Let's see if anyone can solve it.
Is that where the things, the lanthanoids
No, the lanthanoids don't start till here.
Oh,
Okay, let me give you a clue. There is, well, before I do that, let me show you this video.
Ionization energy is the energy required to remove an electron from an atom or ion. It measures how strongly an atom holds its electrons. The first ionization energy, I1, is the energy required to remove an electron from a neutral atom. Considerably more energy is required to remove a second electron from the positive ion. This energy is called the second ionization energy.
Okay, so first ionization energy is the energy required to rip away the outermost electron. Second ionization energy is the energy required to remove the second farthest electron. There's a fourth. Okay, you get the picture. Now let me go back here and let me show you something. Lithium's second ionization energy is 1200. While beryllium's, and I'm making these numbers up, but I'm pretty close. Beryllium's second ionization energy is 350. theories as to why. Ryan, you can have first shot at it.
Do you subtract the first one from the second one?
No, there is no math pattern to this.
Oh,
There is a chemistry reason to it, not a math pattern. Phobos.
And is it because that like the first electron that you take away is really far away, like with lithium it's really far away, so it doesn't take that much energy. But the second one is a lot closer to you.
Yes, that would kind of explain this one. Let's look at lithium. Lithium has the helium inside, and it's 2s1. So when it loses one electron, all that's left is the helium inside, which is good, which is what they want. So how likely is it going to be for it to lose a second electron? Is it going to want to do it at all? No, because that would ruin this. It would mess that up. And now it would be unstable again. It's stable now. It has the noble gas inside. It's stable. It's happy. If it was to lose another one, it would be unhappy again. So, as you can see, it's going to hold on to its electrons significantly. And you're right. It has to do with the fact that this is lithium, and then lithium plus 1, and we'll talk about this, is much smaller. So closer to the nucleus, it's going to be harder to rip it away. Now, first of all, can you come up with a theory as to why beryllium's first ionization energy is so high? Anybody? Why is beryllium's first ionization energy so high? Yes? Yes. Beryllium is helium, which is what it wants to be, 2s2, which is full. It's not great, but it ain't bad. Here, it was 2s1, which was not full, which was bad. So the way it is, it's kind of stable. So does it want to lose one electron? Marie? No. Okay, but if it does lose one electron, now what is it? It's not full. Now it's worse off than it was. So why is its second ionization energy so low?
Now it just has one, so it doesn't really matter. So that's okay.
Now it only has one, and it's going to want to lose that one in order to become more stable. Same thing over here, though it's a little more subtle. What's so different about nitrogen? Why is it harder for nitrogen to lose an electron than it is for oxygen? Anybody? Think it through. What's so special about nitrogen? Actually, everyone in that column. What's so special about it? Yes?
It's right in the middle, so it has the 2s is full, and then 2p is half full, and that's
2s2, 2p3, full, half full. Which ain't bad, ain't great, but ain't bad. Oxygen is helium, 2s2, 2p4. Full, not full, that's a losing hand. So, does it make sense that oxygen is more likely to lose an electron than nitrogen? Yeah. So, that's why you have a little bit of a jump there. And then it comes back, and then it goes back up. Because oxygen won't mind losing an electron there, so that at least now it's half full. It's, keep in mind, this is still pretty high. It's not likely to do it. But of the two, it's more likely to do it. Yes? Yeah. Yeah, of course. You can ionize oxygen. It's just not as likely as these guys, which are really, really low. Okay? That is ionization energy. As you go from left to right, it increases generally with some jumps, like you saw there. Generally speaking, it increases and it decreases as you go down. Okay, so tonight for homework, I'm going to do this. I'm going to give you 4 elements, and I'm going to ask you to place it in some sort of order. For example, I will say place these 4 elements in increasing atomic radius. All I remember is 2 things. I remember what's going on with atomic radius, and then I remember that everything is the opposite. Everything else is the opposite. Okay, so selenium, tellurium, sulfur, and oxygen. Okay, so what you want to do is find these on the periodic table. So look back here with me. Look back here with me. There's selenium. Oh, there's tellurium, oxygen, and sulfur. So they're all in a column. I need to place these in increasing atomic radius. So is that going down or up? Let's see if we can remember. As you go from left to right, it decreases, and as you go down, it increases. Okay, so we're going to have to go from toppest to bottomest. So the answer is oxygen, sulfur, selenium, tellurium. Okay. What if I was to ask you for increasing ionization energy? And here they are. Astantine, lead, iridium, barium. Okay, stop. Ionization energy, what is that? Okay, I remember 2 things. Remember, I remember what happens to atomic radius, and then I remember the second thing is that everything else is opposite. So I changed the question to read what? Decreasing atomic radius. So where are they? They're all in a row. So do I need to go from left to right or right to left? Left to right. That's right. So barium, iridium, lead, and astantine. All right. Decreasing electronegativity. Electronegativity? What the heck is that? Okay, that is a periodic property that we are not going to cover until we get to chemical bonding, which is in 2 chapters. But I remember 2 things, Chris. I remember that what happens with atomic radius? Mortal. I remember what happens with atomic radius. And number 2, I remember that everything else is opposite. So it's not decreasing electronegativity, it's increasing atomic radius. All right, let me give you some of these. It's going to be silicon, tin, lead, carbon. Bethling? Carbon, silicon, tin, lead. Okay? That is ionization energy. Final target. I can determine the difference in radius between an atom and its ion form and the reason for the difference. What is ionic radius? Ionic radius is the exact same thing as atomic radius, but it's the radius of an ion. Basically, what happens when an atom gains or loses an electron? Check this out. You tell me. Give me an explanation for it. Sodium is this big. Sodium plus 1 is this big. Explain. Explain it to me. Does anyone have a explanation? Noah.
Because sodium plus 1 has one less electron, so it'll be small.
Okay. Whenever you're explaining things in this topic, you have to use the words effective nuclear force and or shielding effect. So use one of those phrases. You're right, it loses one electron. What is shielding effect?
It's when there's more and more between the atoms and the air, so it loses attractiveness and...
Okay, so what happens if you lose an electron to shielding effect? Okay, go back to the metaphor. So you're the 19th boyfriend of 19. What if Kate Upton comes up to you and says, hey, you're more than man enough for me. I'm going to lose a boyfriend. I don't think I need 19. I think I'm happy with you and the other 17 guys. What do you think about Kate? Yeah, she's a little more attractive now, isn't she? What happens to the shielding effect knowing now that she has lost a boyfriend because of you? It's weaker. So there's two reasons. Number one, he was right. This was 3s. When you lose an electron, that 3s is gone. But here was 2p, and now the 2p is closer. Why? Because there's less shielding effect. There's less electrons between you and the outer shell, so everyone is more attracted to the nucleus. Does that make sense? Okay, here's magnesium. Magnesium is going to be a little smaller than sodium, and then magnesium plus 2 is tiny. Who can explain that one? Who can explain that one? Silas? Simon, I'm talk. Oh, it's okay, man. I called Elias Silas. I don't know. There's something wrong with my brain today. I'm sorry. Okay. I don't know why I called Elias. I have Silas in the brain. The thing is, I've not. Your brother's called Silas? Okay. I'm calling everyone Silas today. I'm sorry. Ask Elias. I called Phyllis? Call him Phyllis. No. I called him Silas twice. Go, Simon.
Well, when MG loses 2 electrons, doesn't it have like more? Isn't the nucleus more attractive to those other electrons?
Yes.
They come in closer.
There's less shielding effect.
So it's the same thing.
Yeah. So, but now you're losing 2 electrons. So, not only that, but describe Kate here and Kate here. Yeah, because she's fatter.
Wait, can you repeat that?
Okay, remember, as you go from left to right, the nucleus is getting bigger because you're adding protons. Magnesium has 11 protons. I'm sorry, sodium has 11 protons, magnesium has 12 protons. So that the nucleus is already fatter, so it has a greater effective nuclear force. So not only do you lose 2 electrons, which makes a shielding effect, but as you go from left to right, you've gained a proton, which makes it even more attractive.
So if you have sodium and magnesium and they both of them lost an electron, like both of them, you'd rather go with magnesium because it's fatter? So if you were given those two, they would
Right.
the same amount? Okay.
Right.
Awesome.
Okay, so sodium plus 1 is going to be this size. Magnesium plus 2 is going to be smaller. What would you expect aluminum plus 3 to look like? So basically, as you're going from left to right, the more electrons you lose, the smaller you get. How about with the nonmetals? Wait. There's an easier one.
Every single one of those dots.
There we go. Okay. So here is fluorine. And here is fluorine negative. Somebody new. Not Simon, not Noah. Alec, go.
It's bigger because it has an extra electron.
So what would happen if Kate was to come up to you and say, "Hey, I'm staying the same weight, and I'm gaining another boyfriend"? It's not as good. It's not as good. Oxygen is a little bit bigger than fluorine, and oxygen negative 2 is quite a bit bigger than fluorine negative 1.
That's
Actually, fluorine has 9, right? Yes. 9, and oxygen only has 8.
Oh, so it's a lot less attractive.
So Kate is a little smaller, which makes her uglier. And there are 2 extra electrons.
So she has more boyfriends.
Yes. So
she's really ugly now.
to the boyfriends. That's right. Okay, so does this make sense? What about in nitrogen negative 3, where Kate has even lost more weight? She's a smaller nucleus, and she's gained 3 extra boyfriends. Not a good situation. The ENF is lower, and the shielding effect is greater. This sucker is big. This sucker is big. Ionic radius. So the more electrons you gain, the bigger you are. The more electrons you lose, the smaller you are. Okay?
So does no one want to react with hydrogen?
Oh, hydrogen is
All the
very
electrons in an atom are attracted to the nucleus at the same time that they repel one another. The electron shown, one of the outermost electrons of the atom, is partially shielded, or screened, from the nucleus by the other electrons. At the same time, it partially shields or screens the other valence shell electrons from the nucleus. When this outermost electron is lost, the partial shielding it provided for the other electrons is lost. As a result, they experience a greater effective nuclear charge, and the cation, or positively charged ion, is smaller than the original atom. When an electron is added to a neutral atom, it experiences a partial nuclear charge. Because it is imperfectly shielded from the nucleus by the other outermost electrons. At the same time, the added electron contributes to the shielding of the nucleus from the other electrons. The added electron also gives rise to increased electron-electron repulsions. Thus, the anion that results from adding the electron is larger than the original neutral atom.
Okay, so does that make sense? So smaller, 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 smaller. Bigger, 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 bigger. Okay, let's talk about reactivity, because that's not really a property, but it's all interrelated. Basically, folks, remember that the periodic table is separated between metals and nonmetals. The most reactive metal is francium. So the closer you get to francium, the more terrifying you will become. The most reactive nonmetal is fluorine. So the closer you get to fluorine, the more terrifying you will become. And you need to remember that. So the further down and to the left you go, the more reactive you're going to be. The further to the right and up you go, the more reactive you're going to be if you're a nonmetal. Yes?
If fluorine's like bad for you, like how are they using it in drinks and stuff?
My friend, have we forgotten that there is a huge difference between fluorine and fluorine -1? If you use fluorine in any way, you use fluorine -1. Okay, iodine you can put on the palm of your hand and play with it. It'll stain your skin. It may irritate your skin. Bromine is going to be a liquid. You can keep the puddle there. It'll probably damage your skin. Go up to chlorine is a gas. Take a nice deep breath. Your sinus passages will start bleeding. You'll start coughing. And you might actually, if you breathe enough of it, you'll start coughing up blood. Fluorine, you take a nice deep breath, you quite possibly will die. Yeah. So as you go up, it becomes more terrifying. Let's let Brainiac, which is a British show. Have you seen Brainiac in Britain? No. This is a BBC show where they do all sorts of crazy science-y type things.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a response...
Okay, so notice that the girl with the cut-off shirt and the tight little pants, she is representing lithium, and lithium, it makes a teeny tiny little fizzing, kind of like Alka-Seltzer in water. Now what happens when another woman is introduced?
Adults have mixed H2O.
Now that is ageism. Why? Yes, that's a woman. That is ageism. That is ageism. And why she doesn't have the little cut-off shirt and the tight little pants is ageism.
No one's attracted.
With sodium.
Okay, so now we're seeing a little fireball. That's sodium. Now we're going to go down to potassium.
And you may, under very strict scientific control, have witnessed potassium mixed with water.
Okay, so now we see a definite fireball and an explosion.
But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate. Present. Oh, thank you. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
All right, so as you're going down the column, it's becoming more and more terrifying. What will cesium do?
Yes. Wow. That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
I noticed two things today about the megaphone that he's about to use. Number one, why is he using it? He's the one that's holding the very dangerous cesium. And number two, watch what he does with the megaphone, which has to cost money. Watch what he does.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
How hard would it have been for him to carry the megaphone with him?
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
Now, I have some bad news for you, because the guys, the Americans at Mythbusters, just suspected that there was something funny going on. So they tried this experiment, and they could, I mean, it was definitely an explosion, but not nearly big enough to explain the destroying, the bathtub destroying. So then Brainiac admitted that, yes, they weren't getting a satisfactory explosion, so they added some dynamite to the sides of the tub in order to have a much more effective explosion. So, yeah, they admitted they fudged it. But the concept still remains. As you go down the column, it becomes more explosive. Okay? So,
What does
do
the F one look like when it explodes?
francium?